Hi everyone, today we're going to talk about how you can complete the square. It is yet another method that we can use to solve a quadratic equation. And we usually will try and use this method when factorization fails. And that's when, you can change it into binomials to figure out the answer. Sometimes we can't do that. So completing the square is a method that we go to. Completing the square basically comes from the fact that any quadratic equation can be written in the format x plus p squared equals q, where p and q are just real numbers, normal numbers. It does require you to manipulate the equation a little, okay? But let's start off, before we even solve this example 4 from the book, let's just start off with a very basic equation with a square. X squared equals 49, for instance. Okay, so we're ignoring this for now. If I were to solve this problem, you should know by now that the opposite of squaring, if we were trying to get rid of the square and get it down to just an x, would require us to square root both sides to keep it equal. The square and the square root cancel, so x would equal to the square root of 49. Now, two different values can get us to 49, so therefore the square root of 49 is both possibly a positive or a negative. It can be a positive or a negative 7, because 7 times 7, 7 squared, is equal to 49. But then negative 7 multiplied by itself, squared, is also 49. So we do have to keep in mind that the square root of a positive number, because you can't, not at this point at least, square root a negative number, the square root of a positive number would require you to consider that there are two possibilities, a positive and a negative answer. All right. So going along with that, let's look at example 4 from your book. We need to solve the following equations. A has x plus 3 squared to equal 16. B is x minus 2 squared equals 5. We're going to follow the same concepts, okay? The same thinking. So starting with A, we have x plus 3 squared to equal 16. Just like before, we're going to take the square and we want to unravel that. We want to square root that to cancel it out. So then that means the other side has to be square rooted. So now I have x plus 3, what was left over inside, because those canceled, equals the square root of 16. We know that it's going to be a positive or negative answer, and 16 is actually a perfect square, and that equals, the square root of 16 is 4. Okay, so I have x plus 3 equals positive 4 as possibility, or x plus 3 could equal negative 4. So I have two answers, two possible answers. Subtract 3 on both sides to get x by itself, x equals 1. Subtract 3 on both sides for this equation, x equals negative 7. Both are possible answers. The answer could be 1 or negative 7 to get you to that answer of 16. Okay, same thing with part B. See if you can pause that one and pause the video and try that one on your own. Okay, B. Same thing like before. We are going to square root to cancel that out. So I'm left with x minus 2 equals a positive or negative square root of 5. Here I don't have a perfect square. 5 is not a perfect square. It's going to be a messy decimal number. And if you don't trust me, here we go. Square root of 5 is that. It is an irrational number that goes on and on and on with no repeating pattern. So we're actually going to leave it like that for now. And we're going to go ahead and set up our two equations. So we have x minus 2 equals positive root 5. And we also have x minus 2 equals negative root 5. Okay, so we have plus 2 to both sides, and we end up with x equals 2 plus root 5 for one possible answer, and we have x equals 2 minus root 5 as another possible answer, which again, you can keep like that. It's actually more accurate because you're not rounding or anything like that. If, however, the problem wants you to actually find it in decimal format, then you can do that. And let's say we round it to, I don't know, the nearest hundredths place, so 2 decimals after. Then you could put that into your calculator, square root of 5 plus 2, round to the nearest hundredths place, 4.24 now. Approximately 4.24. And then 2 minus root 5. Let's see, root 5 is this. So 2 minus that. Let me see if my calculator can do that. Nope, doesn't really like that. Let's see, 2 minus square root of 5, or square root of, oops, I didn't even put square root of, all right, square root of 5 is this. 2 minus that. 2 minus 2.236, how about that? 2 minus 2.236, it's going to be rounded anyways, negative 0.236, negative 0.24, okay. So that's only if they want the decimal version of it. But other than that, you can keep it with the square root, the radical. Okay, so what does this have to do with your quadratic equation, right? Well, sometimes you're going to have a problem given to you in this format where you have x squared plus bx. You don't have the c part. And then you're going to have to basically find a constant c, which you can add so that you can then make into x squared plus bx plus c format and create a perfect square so that later you can, figure out the two binomials. Okay, so let me give you an example. So our objective, the goal, is that we need to make x squared plus bx a perfect square in the format x plus p squared. Okay, so here is the problem. They're giving you x squared plus 6x. And you need to figure out the answer. But clearly, normally, you could only make it simple or simplify it by taking out a GCF, and that doesn't really quite help you in most cases, okay? So we need to figure out the missing c value, okay? If I were to illustrate it with my algebra tiles, this is what it would look like. X squared plus 6x would be partially there, okay? We would have x plus 3 times x plus 3. However, x plus 3 times x plus 3 would actually be x squared plus 6x plus 9. So it's basically missing that 9, right? We need that plus 9 at the end that the problem doesn't give us. So in order to complete the square, we need to think to ourselves, okay, well, if I were to look at just the area that I have with my x plus 3 times x plus 3, I have x times x, which is x squared, I have 3 times x, which is my 3x. I have 3 times x again, another 3x. And what I'm missing is the 9. So I can complete the square by adding something squared, right? I need to figure out what it is that's squared. Well, if I needed the 9, it would really be 3 squared. 3 times 3 gets me that missing 9 piece. So then the area, once I add the 9, would become x squared plus 6x from here plus 9. And then I could figure out the perfect square, because this is a special product, x plus 3 squared. Okay, so I need to figure out what I need to get to. Now, how do I figure out the 9 normally without drawing this picture and just getting x squared plus 6x? We'll start thinking about how you can get just from this information to that 9. How is the 6 related to that 3? And you can start thinking to yourself, how does that 6 relate to that 3? Well, it's half of it, right? 3 times 2 will get me to that 6. But let's see if that works in another example. All right, so in this example, I have, again, part of the equation, or the quadratic expression that I want. I have x squared plus 8x, because my area is x squared plus 4x plus 4x. That's all I have. X times x, x squared, 4 times x, 4x, 4 times another x is another 4x. So I just have x squared plus 8x. I need to add another term at the end, my c value, in order to complete this square. So I need to figure out what it is that I should add. Well, what's missing is the 4 times 4, which is 16, right? That's what we need. 4 squared. We need to add 4 squared. So that now my area could be x squared plus 8x plus 16, because 4 times 4 is 16, and then that's a perfect square. Then it would be x plus 4 squared. Okay, so did our halving of the b value work? Well, it looks like it did, right? Because 4 is half of 8. So there it is. That's the completing the square method. We're taking our b value and we're dividing by 2 to get that number. But remember, we have to complete the square, so it's got to be squared. Okay? So that's how people came up with the completing the square method. In general, and again, this needs to go in your notebook now because this is the completing the square method. To make x squared plus bx a perfect square, because we were missing that little chunk, we add the b value divided by 2 squared to it. So then therefore x squared plus bx plus half of b squared would then help us get to the perfect square of then x plus b over 2 squared. Okay? So if you notice up here, that's how we got there. We took the b value, because this was originally 8x, right? We took the 8, divide by 2, which is 4, and then 4 squared is 16. So then that's how we ended up with x plus 4 squared as our answer. Okay, so this 4 here, this b over 2 squared, helps us complete it, but it also gives us the actual answer in our binomial, that 4, which is just the b value cut in half. Okay, that's what they mean by x plus b over 2 squared, right here. Okay, and now notice, in order for this to work, the coefficient of x squared has to be 1. If there is a number in front there, then it's not going to work, right? Because it's a perfect square. Okay, so be sure that this is in your notebook. And now we're going to do some problems. So first off, we are going to practice how to find that constant term, that c value that needs to be added. Okay, so here we are finding the constant term that must be added to each of the following expressions to obtain a perfect square. Go ahead and pause the video and try it on your own first. All right, so for A, remember in order to figure out that constant term that needs to be added, we're taking the b value, the b is 3, divide by 2, and then we are squaring it. So it ends up being 9/4. So 9/4 is what we need to add in order to complete the square. For b, y squared minus 10y, okay, we need to take that b value, -10, we need to cut it in half and then square it. So we end up with -10 times -10 is 100. 2 times 2 is 4. So that's 25. 100 divided by 4 is 25. Or you could have saw that this is -5. Square that. And then you get 25 as well. Okay? So that's how we would figure out the missing c value. And then once you figure out the missing c value, then you can actually break it down into binomials. So we can actually do that here. Now that this has become x squared plus 3x plus 9/4, we can actually break that down into a perfect square problem, and it's just taking the b over 2. So this becomes x plus 3/2 times x plus 3/2, just like how it says up here. Okay, and then we have our two binomials. Easy. Same with b. Now that I have my c value, I can break that down into my two binomials because I have y squared minus 10y plus 25 now. And that is the same as x plus my b over 2, or minus, in this case, squared, multiplied twice. Yep, just like that. So all it was missing was the c value. Okay, now, if it's in an equation, it's a little bit different. Solving a quadratic equation by making that expression x squared plus bx a perfect square is called the completing the square method, and we can use it to solve for our missing x value. So let's look at example 6 from the book. Solve the equation x squared minus x minus 3 equals 0 using the completing the square method. All right, you're probably looking at this and thinking, there is a c value. I don't understand. What's wrong? Or why can't I just factor it, right? Well, let's try factoring it. Are there two numbers that can multiply to get to -3, but then add to get to -1? Well, I have 1 and 3, but 1 and 3, if you add them, it's 4. If you subtract them, it's 2, right? So it doesn't really get you to that -1. So factoring doesn't work. Okay, that's when you know, okay, I'm going to have to take out the completing the square method because normal factorization doesn't work here. All right, so we are going to add the 3 to both sides because we don't really like that constant at the end. It's doing nothing for us. So we're going to get rid of it. Now we can focus on figuring out how we can complete the square to then create our two binomials at the end. Okay, so I have x squared minus x. Don't know what we have to add at the end, but it's going to be our b value over 2 squared. My b value is a -1. So it's going to be -1/2 squared. That's what we're going to add to both sides, because we have to make sure that things are balanced. So we end up with x squared minus x plus -1/2 squared equals 3 plus that -1/2 squared. We'll deal with that later. All right, now that we're here, I'm keeping it, I'm not simplifying this -1/2 squared because it basically tells me how I'm going to break it down. So I really don't need to change that into 1/4, right? If I'm gonna end up breaking it down into two binomials anyways. So it becomes x minus 1/2 times x minus 1/2, which is really x minus 1/2 squared, okay? And that's how we can complete our square on the left-hand side. Over here, I might want to actually break it down and simplify it. -1/2 times -1/2 is a +1/4 because top times top, -1 times -1 is +1. 2 times 2 is 4. And this becomes 3 1/4. Okay? So now I have an equation that has two binomials, and I can now set up two equations on the side to then figure out my final answer. Okay, so let me do that here. X minus 1/2 square rooted means I have to, squared means I have to square root to get rid of that. So now x minus 1/2 is what's left over, equals square root of 3 1/4. Now remember, it could also equal the negative version of that. So I actually have two different possible answers. My first one can add 1/2 to cancel, second one as well. So I end up with x being equal to 1/2 plus square root of 3 1/4, or 1/2 minus 3 1/4, the square root. Okay, let's start off by getting rid of this 3. I'm going to add it to both sides. I'm getting rid of it because it's doing nothing for me. I couldn't factor it. And then now I can figure out the completing of the square. I need to figure out what constant I need to add in order to complete the square. That would be b over 2 squared. My b value is a -1. That's the number in front of my x. So -1 divided by 2, square that. I'm going to keep that as it is. It's going to help me out later over here. And I'm going to add that to both sides of my equation. Because it's an equation, I have to keep it balanced. Whatever I add to one side, I have to add to the other. So now I have x squared minus x plus -1/2 squared equals 3 plus -1/2 squared. I'm going to keep it as it is. I'm not going to actually change it into 1/4. -1/2 times -1/2 is 1/4, because I'm changing it into a pair of binomials anyways, which is x minus 1/2 times x minus 1/2. So there's really no point in changing into 1/4. This one I can change into 1/4 because I will actually be doing some math with that. I can simplify this to x minus 1/2 squared equals 3 1/4. Okay, now that I'm here, I am one step closer to now figuring out my answer for x, because I have two binomials. And I have x minus 1/2 squared. So in order to get rid of that square, I can now square root it, because that's going to be the opposite. I need to do that to both sides. And now I'm left with x minus a half equals the square root of 3 1/4. But remember, the square root of 3 1/4 can be positive or negative. So I had to set up the possibility that it could be a negative answer. And then in order to get x by itself, I am going to add a half to both sides. Cancel, cancel. So I end up with a half plus square root of 3 1/4, or x equals a half minus square root of 3 1/4. Those are my two possible answers. The positive and the negative version, the adding and the subtracting version. Now, if you wanted to go further and let's say you're like, this means nothing to me, I need an answer that's I can actually use in real life, you can put that into your calculator. So figure out the square root of 3 1/4, which is 3.25. Square root that, it's about 1.8. So if I'm adding a half to 1.8, 0.5 plus 1.8, this is obviously estimated because we rounded, it'd be about 2.3. This is if somebody wanted it in decimal format. This radical format is fine as well. 1.8 was the approximation, right? So this one would be 1/2 minus 1.8, 0.5 minus 1.8, and that would be about negative 1.3. Okay, so those two work as well for answers. Okay, let's do one more example from the book. Here's example 7. Solve the equation 3x squared plus 18x plus 2 equals 0 by completing the square. Go ahead and pause the video and try it on your own first. Okay, so we need to use completing the square method here because normal factorization won't work. So before I use completing the square though, I notice I have a digit or a number a coefficient in front of the x squared that's not 1. So I can't complete the square until it is a 1. I'm going to go ahead and divide it by 3, but in order for this equation to stay balanced, that means I need to divide everyone by 3 so that it's balanced. 3 divided by 3 is 1, so I end up with x squared plus 6x plus 2/3 equals 0 divided by 3 is 0. Okay. And I'm going to move this 2/3 to the opposite side because it's doing nothing for me. So I end up with x squared plus 6x equals negative 2/3. I'm leaving a space here because I know I'm going to be completing the square and adding something there, so I might as well leave a space for it. If I have x squared plus 6x, in order to complete that square, I need to find b over 2 squared. My b value is 6, so 6 over 2 squared. 6 divided by 2 is 3, so it's 3 squared. So I need to add my missing c value to complete the square, which is 3 squared. Okay, so then this becomes x plus 3 times x plus 3, right? Because 3x plus 3x will give you that 6x, and 3 times 3 will give you the 3 squared, which is 9. So there wasn't really any purpose of me simplifying that to 9 because it already shows me that factor that I needed. All right, so I do need to change 3 squared to 9 over here though, so that I can figure that answer out, that addition. Change this to a square. 9 minus 2/3 is the same as, let's see, 9 is the same as 27 thirds. Actually, let's change it to 8. 9 can be changed to 8 and 3/3, right? Because 8 plus 3 over 3 is 8 plus 1 minus 2/3. So this would be 8 and 1/3. 8 and 1/3. Okay, and I need to get rid of the square, so I'm going to square root it, square root both sides, and then I can start solving my problem. Let me use this left-hand side here to solve. So then I end up with x plus 3 equals the positive square root of 8 1/3. And I also have the possibility that I'm going to have a negative 8 1/3. Negative square root of 8 1/3, I mean. Okay, and then we're going to subtract 3 from both sides to cancel. So then at the end, our answer would be x equals, let's put negative 3 plus the square root of 8 1/3. I like to switch them because I don't like that this minus 3 is hanging out behind that square root, because it could accidentally be kind of put under the umbrella of the square root sign. So I like to keep it completely separated from my square root sign. Same over here, x would equal to negative 3 minus the square root of 8 1/3. I don't even want anyone to possibly consider that that 3 is underneath the square root sign. Okay, so these are our two possible answers, slightly different from each other. Now again, you could put them into your calculator and figure out the approximations with decimals. Let's see, 8 1/3 would be 8 with 3's repeating at the end. Oops, it doesn't even like that many. Actually, let's do, yeah, 3's repeating. We're going to square root that. So let's just approximate it to 2.9, okay? So it's negative 3 plus 2.9. It's going to be an approximation. Negative 3 plus 2.9. That's the downfall of it, negative 0.1. The downfall is that it is an approximation. The benefit is that you can actually use this number to do stuff. I already forgot what the square root is. 2.9, right. So this one is negative 3 minus 2.9. Negative 3 minus 2.9. Negative 5.9. Okay, so approximations in green and the accurate radical answer in blue for you here.